turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast. This is the programme that brings you the biggest breakthroughs and also talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith, and today we are going nuclear to examine the science and politics of some of the most powerful weapons of mass destruction ever invented. This programme was first published on the 11th of November, or Armistice Day, a moment not only to reflect on the devastation of conflict, but the fragility of peace. 2025 is particularly poignant because it marks 80 years since the end of the most costly war in human history, which concluded when the United States dropped 2 atomic bombs on the Japanese cities of Hiroshima and Nagasaki. The gruesome power that these weapons unleashed was the culmination of the Manhattan Project, itself driven by rapid developments in science and technology. It remains the only time they've been used in warfare, but the creation of nuclear weapons of mass destruction set in motion an arms race that persists to this day. So how did we get here? After the bombs fell on Japan, an arms race ensued as competing nations fought to develop successively more powerful munitions, starting first with atom-splitting or fission-powered bombs, and then subsequently evolving into fusion-powered, so-called hydrogen bombs. Alex Wellerstein is an historian of science at the Stevens Institute of Technology, and he's a visiting researcher at Sciences Po in Paris.
So nuclear fusion was actually discovered before nuclear fission because that was the explanation of how the sun worked. And once people started talking about fission bombs and the amount of energy released and the amount of heat released, there were numerous people who said, hey, you're talking about energy releases that are on par with the sun. Even if they're very brief, could you fuel a reaction like the sun, a fusion reaction? So could you take the energy of splitting atoms, big heavy atoms, and use it to squeeze together light atoms like those of hydrogen and get a lot of energy as well? So even as they were working on the first fission bomb, scientists in the United States were already thinking about, well, what if you added a fusion component to this that would allow you to potentially multiply the energy release of even a very large fission bomb by a factor of hundreds or even thousands.
And this is the testing that then happened in largely the 50s, wasn't it? There was a lot of remote testing in remote and beautiful places that took place around the world and actually caused a big spike in radiation around the world in the aftermath.
After the Soviet Union detonated its first bomb in 1949, there was a very intense debate within the classified community in the United States, and eventually it leaked out into the public, over whether this hydrogen bomb, what they called the super, should be the next step. The United States decided to pursue this, and it turned out to be harder to do than they expected. It's not as easy as just throwing hydrogen in with a fission bomb, but they were able to test a device, they would call it. It wasn't weaponized yet. You couldn't drop it out of a plane in 1952, and they tested one that you could drop out of a plane in 1954. And these weapons are intensely radioactive because the fission part of the bomb is the part that creates the most radioactivity in nuclear fallout. And fusion doesn't really create that. But what they do in these weapons, especially these early ones, is they take the fusion, it generates neutrons, which can create more fissioning. So in the end, even a fusion bomb is really about at least 50% fission in its output, which makes it much more contaminating than a normal, Hiroshima, Nagasaki style atomic bomb. So the testing released just huge amounts of radioactive material. Some of that came right back down again and contaminated islands and anybody downwind. Some of that went into the upper atmosphere and circulated around the entire planet, and people got very small but detectable increases in their background radiation exposure.
one serviceman who I met once. I think he's probably died now. He was very old at the time, but he was standing on one of the beaches watching this, and he said they were asked to cover their eyes, and he said he could see all the bones in his hands. It was so bright and powerful when it went off.
There are pictures from one of these tests that I find remarkable, where if you look very closely, you can see these little spots that sort of flame up in smoke, and those are birds that have been set on fire by the initial heat wave of these multi-megaton weapons. That level of heat is not something that we typically experience on Earth. This is something that puts you in the realm of like volcanoes and meteors and other large-scale phenomena.
As all this was evolving, was the intention that you have something that you would throw at a foreign country and basically devastate that landmass? Or was there a strategic element to it where people thought, well, hang on, bigger isn't always better? Maybe having something powerful but more compact and more limited in what it could do might also be useful.
There ends up being sort of a sweet spot for what's a bomb that will do a reasonable amount of damage, say 15 to 20 times the strength of the Hiroshima bomb, right? So that's a lot of damage still, but can fit in a relatively compact shape. So something that's maybe the size of a large trash can. And then you can put one of those on a missile, or maybe you can put 12 of those on a missile if you really want to get clever about it, which they do. And so you end up not with bigger is better. So there's this period in which bigger is very exciting. And then gradually, especially as you start shifting more towards missiles as the delivery system, you don't want a bomb the size of a school bus. You want a bomb that's easier to get from point A to point B. So the sweet spot ends up being bombs that are around 100 to 500 kilotons, so under a megaton. For reference, Hiroshima is 15 kilotons. That sweet spot is when you've really engineered it so that it's easy to put this bomb on what they would call a delivery vehicle, a very euphemistic term for a missile or something like that.
Alex Wellerstein at the Stevens Institute of Technology and Sciences Po in Paris. The technology that Alex was just discussing emerged from the 1940s Manhattan Project, which was a vast, secretive wartime initiative that marshalled scientists, engineers and industry, as well as the military, to turn abstract theoretical physics into devastating reality. Robert Oppenheimer's work, of course, culminated in the Trinity test, which paved the way for the first and last atomic bombs used in anger. But what is that science that underpins the devastating power of these weapons? We put in a call to Cambridge physicist Ben Allanach.
To discuss all this, we really need to just remind ourselves what the nucleus of an atom is. It's the small centre of atoms, protons and neutrons, stuck together with the strong nuclear force, which sticks them together in a sort of ball in the middle of the atom. You're trying to liberate some of their energy, which is a huge amount of energy that's stored in those nuclei.
And so when you unleash the energy, what happens to the nucleus? And how does the energy then get converted into explosive or destructive forces?
What you need to do is cause a nuclear reaction, which splits one big nucleus up into two smaller ones and, say, 3 neutrons. That process of splitting them up is called fission. And the energy that's stored by sticking these particles together originally in the nucleus, that ends up as kinetic energy of the neutrons. So they're traveling quite quickly, and that will heat up the surroundings and so on. And then there's another way of having a nuclear reaction, which is where you somehow stick 2 nuclei together to form a larger one, and that can liberate even more energy, and that's called fusion because you're fusing 2 nuclei together.
So in the first example, if we split a nucleus apart into daughter nuclei, which are smaller than the parent they came from, then it takes less energy to stick the nuclei in those daughters together, and the difference is what gets released. So why is it then, when you do the opposite and fuse things, that in fact building nuclei together takes less energy? Is there a sort of sweet spot then where up to a point it takes less energy and then it starts to take more, which is why the two processes differ?
Yeah, indeed. There's a certain size of nucleus, which is actually iron, which is the crossing point. If you're fusing smaller nuclei into a larger one that isn't too large, that it's not above iron, then you will liberate more energy than the other way around. So fission bombs were the original ones that were invented, and they're based on this breaking up of the nuclei. And so the classic one is with uranium-235, So this is a nuclei with 235 protons and neutrons in it. And that will break up into 2 smaller nuclei and 3 neutrons. That process can be stimulated by a neutron hitting the uranium-235 nucleus. So if you're producing 3 neutrons from each one of these, then of course each of those neutrons can hit another nucleus and stimulate another breaking up of another nucleus. And you get this chain reaction, which will go throughout all of the uranium, essentially.
So one splits, that liberates 3 neutrons. Those 3 neutrons split 3 more atoms, which release 3 more neutrons. So you go 1, now you've got 9, then you've got 27. So you've got it growing very, very rapidly, how many nuclei it can split, which is the chain reaction that then feeds back on itself, releasing a huge amount of energy very, very quickly.
An incredible amount of energy released in a relatively small volume very quickly. That's an explosion.
If the ingredients for the bomb are there and they're just spitting out neutrons like that, how do you stop it going off before you want it to? What do they actually do to make it so that it's predictable when that chain reaction is kicked off?
There's an amount of uranium, which is called the critical mass. And below that amount, it won't actually go off. What's happening is each individual uranium nucleus has a chance of decaying, but it decays very slowly. Its half-life, that's the amount of time it would take for half of it to decay, is hundreds of millions of years. So each individual nucleus is very unlikely on its own, without a stimulated neutron hitting it, to pop. So what they do is they have 2 smaller bits of uranium in a nuclear warhead, and at the time they want it to go off, they'll put explosives, conventional explosives around them and blow them together, so that you get this above the critical mass, and then it will go off very quickly.
And what about with the fusion bomb?
You have a 2-stage bomb. You set off the nuclear fission, and you use incredible temperature and pressure from that reaction to fuse the other nuclei that are there together and get the fusion to work. It has incredible amounts of destructive power. If fission bombs are measured in 10,000 tons of TNT equivalent, the fusion bombs go up to 50 million. I mean, it's really a step up.
What about the radiation produced from this? How much of it is there? And is this analogous to what happened in Chernobyl when the nuclear power station blew up? Do you get a similar sort of level of damage and fallout from that? Or is it worse? Or can it be mitigated? How does it work?
When the bomb actually goes off, there's a lot of gamma radiation. So that's essentially electromagnetic. So, you get the visible flash, but there's also an invisible flash of electromagnetic radiation. And that will go through everything. But the more dangerous aspects are that you're producing all of these different nuclei that are maybe radioactive in themselves. So you produce various isotopes of nuclei in these reactions, and they can pop. They can just undergo spontaneous fission, and their half-life might be thousands of years or even hundreds of years. So if you get that stuff on you in the radioactive dust and so on, then that's not good, because you've got something very close to you, which is producing energetic particles. And radiation essentially acts as a nuclear bullet. It can go into, for example, bits of your DNA and change it. And if you get an unlucky change, it can promote it to be cancerous.
That's on the understanding, of course, that you survived the blast in the first place, I suppose, because the initial effect is going to be that massive release of energy, which that's going to be very, very hot, isn't it? So is most of the destructive effect because you've got this very, very high temperature blast, effectively?
That depends on how close you are to the blast epicenter, how powerful the bomb was. Yeah, indeed.
Ben Allenach there.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientist podcast with me, Chris Smith, and today we're going nuclear to explore the science and politics of atomic weapons of mass destruction. Now, currently, 9 nations possess nuclear weapons, but they've still only been used in combat twice, when US President Harry Truman gave the order to drop 2 separate atomic bombs on the Japanese cities of Hiroshima and Nagasaki in 1945. So which countries currently have them, And how likely might they be to use them? Well, Michael Clark is a defence analyst with Sky News.
Russia and America both have about 1,500 weapons pointing at each other. And China has got about 600 and will not talk about arms control until they get to about 1,500. So those are the big three. Then the next two who are part of the old system are Britain and France, who deploy just minimum deterrence they have about 200 weapons, but they only deploy about 40 or 50 of them because that's all they can afford to deploy for their last-ditch defence. And then below that, you've got the other difficult cases where they haven't signed an arms control treaty, they've just gone for it themselves, and that is Israel has got its own nuclear program, probably got about 200 weapons. India and Pakistan, weapons pointing at each other, and they've probably got about 40 or 50, enough to devastate each country, but that's roughly the number. And then there's North Korea, the ninth one, who's an outlier, and they've also probably got somewhere between 20 and 60 usable devices, and they point them at absolutely everybody because nobody quite knows what North Korea is doing.
When you say that people have got warheads numbered in the thousands, do they really need that many? Surely there's enough firepower there to completely destroy the planet many times over.
Yes. I mean, the good news is that the 1,500 that they deploy at the moment against each other, the United States and Russia, is far less than they used to deploy. They drew them down from way over 2,000, almost 3,000 each, down to 1,500 each. And that's the figure that they say they feel comfortable with, because if a lot of them didn't work, or if they were undermined in some other way that they couldn't deploy them, that something else went wrong, there are enough there to completely devastate the territory of the other country. So it's over insurance. With 1,500, they feel that they could never be undermined, and that's probably true. So they say that, high numbers give a sort of low threat, because if the numbers are so high that you relax, you've got plenty, and nothing that the other side will ever be able to do would negate your ability to hit them back, to retaliate and destroy their country. So it's regarded as an example of stable deterrence. And though the numbers seem ridiculous, there is a sort of a strategic logic beneath them, which says if we've got really high numbers, nobody will even think about taking us on.
How modern are these weapons? Because I've heard various things from various quarters over recent years where people are saying some of these weapons are actually really old and we don't even know if they'll work.
Believe me, they're tested all the time in sort of simulated conditions. It's called bench testing. They're bench tested a lot. I think there's a great deal of confidence that the warheads, they really would work. What is not so clear is the delivery systems, because they're being upgraded all the time. Some of them are delivered by aircraft, and aircraft are changing all the time. Some are delivered by missiles. They change a bit more slowly, but they are always being modernized. Some of them are down to artillery shells, some small nuclear weapons, tactical nuclear weapons as they're euphemistically called, are fired in literally artillery shells, artillery rounds, 155 millimeter rounds. And so it is the case that the delivery systems might fail, and the warheads are in design terms very old, but nobody, and honestly I'm sure about this, nobody thinks that the warheads would not work if they were required to be used, because all of the serious nuclear powers, like Russia, America, Britain and France, those are the serious powers, are constantly testing and checking these things. And nobody, believe me, would take the risk of attacking, hoping that the other side's weapons didn't work. That's inconceivable that anyone would try that.
And when would someone consider actually using this? What are the protocols? What lines have to be crossed for us to start hitting that big red button?
Well, that's the really interesting and scary part of it. For years, we lived through an era, most of my lifetime, in fact, and I'm quite old now, the view was nuclear weapons would only be used as a very, very last resort. If we thought that our whole society was going to be devastated, then we might use them. They're a weapon of absolute last resort. Sadly, now we find that we've got powers, particularly in Russia at the moment, who rattle their nuclear weapons. They threaten. And so what we've seen is the idea that nuclear weapons are last resort weapons has been, as it were, squeezed out a little bit to the idea that, well, maybe in a war for something important, not necessarily the problem of extinction, but a war that's just important, we might end up using tactical nuclear weapons. And if we use tactical ones, small weapons, then very quickly we'll end up using big ones. So the situation now is actually conceptually a lot more dangerous than it was, say, even 20 years ago.
So, if for the sake of argument, Vladimir Putin did deploy some tactical weapons of the smaller caliber, let's call them, that you mentioned earlier, these 155mm rounds, for example, that you could fire like an artillery shell, that wouldn't necessarily incite a nuclear response from other parties then. Just because a nuke has been deployed, we don't have to fight fire with fire, but it might raise our heckles to the extent that we would consider doing something like for like.
That's exactly true. And I mean, this prospect arose a couple of years ago when Putin was being very reckless in the things he was saying. And it was made very clear to him through several sources. If you use any nuclear weapons in Ukraine, and you'd have to use more than one to have any battlefield effect, they'd have to use 5 or 6 weapons of about the Hiroshima size, the size that we used in 1945 against Hiroshima and then Nagasaki. If you use any nuclear weapons like that in Ukraine, we the Americans, this is Joe Biden's administration we're talking about now, not Donald Trump, but we the Americans would probably, we would attack all of your bases from which you'd fired those weapons with conventional weapons. We'd destroy the Black Sea Fleet. We'd go after all of your bases. We'd conventionally take out all of your tactical nuclear weapon capabilities with our conventional weapons. We won't go nuclear, but we will attack you in such a way that you would actually regret having used them. And of course, then the onus is on you. Well, what are you going to do about that? And of course, that would be a very, very dangerous situation. But it does prove the point that you just made, Chris, that the single use of nuclear weapons on the battlefield, as it were, wouldn't necessarily mean that the other side would go nuclear. The other side, whoever the other side are, would have an enormous incentive to try to respond forcefully in ways other than nuclear. And of course, only the Americans have really got the power to do that in the current international environment.
Michael Clark at Sky News. Thanks, Michael. The US and USSR came perilously close to open confrontation during the Cuban Missile Crisis in 1962, and then again during the NATO Able Archer exercise in 1983. In both cases, nuclear conflict was ultimately avoided through sustained dialogue and efforts to ease tensions. But what measures actually exist to prevent the onset of a nuclear war? Paul Rogers is Emeritus Professor of Peace Studies at Bradford University.
We've used diplomacy where we can to try and decrease tensions when tensions are obviously going up. But there are more extreme methods, if you like. After the Cuban Missile Crisis, which was a pretty near miss back in 1962, within a few months, President Kennedy made offers to the Soviet Union to ease the tensions. And the Soviets actually replied, not necessarily in completely the same way, but broadly speaking, to lower tensions. It was known as GRIT, Graduated and Reciprocated Reductions in Tension. And it gave us the hotline between Moscow and Washington back in 1963. And it led on to some of the early attempts to get arms control going. And it was probably responsible for the Non-Proliferation Treaty, which came out just a few years later. There are, in extreme circumstances, 1 or 2 other areas where there are the equivalent of hotlines. There is one which was established, I think, just about 20 years ago between Pakistan and India. It's not perfect, it's a long way from perfect. And one of the problems at present is you have every one of the 9 nuclear powers either expanding or improving their nuclear weapons and essentially looking to the possibility of relatively small nuclear wars. Small nuclear wars in far-off places are often considered to be the real dangerous situations. That, I think, has increased in recent years.
To a certain extent, though, with things like this, where we think their value as a weapon is as great when they're not being used, they're just there and could be, as they are if you actually use them. In fact, there's a huge downside, as we all know, to potentially using them. So to some extent, you actually want to promote how many you've got and say you've got loads. It's not like a secret weapon that you don't tell anyone about because their power is their visibility.
I think there are broadly 2 views on the whole thing. One is that nuclear deterrence is stable. Another is that it isn't, and we've been extremely lucky. Indirect evidence of the latter actually comes from an unusual source. Some of the key figures in the Cold War in the West, like Robert McNamara, Kennedy's Secretary of Defense, General Lee Butler, who was the head of the American Strategic Nuclear Weapons, and even Henry Kissinger, after the Cold War, all of them actually became committed to the idea of getting rid of all nuclear weapons. And I think that's because of their experience. They did not buy into the idea that it is permanently stable. And one has to say that almost all the countries engaged in this game do not have no first use policies. Britain's policy, as NATO's is to use nuclear weapons first in extremis and not to wait to retaliate. So the idea, of course, of stable deterrence, it's controversial matter among people who look deeply into these things. And the other thing I think one would say is that there's a useful acronym here, AIM, and that stands for accidents, incidents, and mavericks. All the kind of sort of unplanned things that at a time of crisis between two nuclear powers might lead us into more dangerous situations. And I think this is one of the reasons why people who look at this from a peace research angle are very strong in saying we cannot assume that nuclear deterrence to last. We've been lucky so far. We have to take much more positive moves to get rid of it. If we can do, then the future looks good. If not, then who knows?
Do you think it's realistic, though, to aim for that? I mean, obviously we can aim for it, but do you think it's ever going to happen? Because it's a bit like smallpox has been eradicated from the entire world, but there are two freezers. One is in America, one is in Russia, and neither wanted to be the other to be the only holder of one of the world's most feared infections. Are we not going to be in a similar sort of situation with these deterrents indefinitely?
We could be, and I think that is a pretty realistic way of looking at it. The point here is that actually idealistic in reality? And I think that's a question which is very well worth asking. There are ways in which one can get things down. It's what's known as the web of deterrence. You actually scale things down by agreement. And the ultimate aim would be to have maybe a tiny handful of countries with basic stocks, and then those go into some sort of international agreement under the UN. That's a very long way down the road. But on the other hand, the dangers of nuclear war are so extreme, and there are a couple of very interesting films coming out on this at the present time. I think we really have to think more seriously. And I would certainly say you should listen to the people, including the people in CND, who've been arguing this for a long time. It would be great to think we can do this forever. Personally, I very much doubt it, and I think there is a risk.
Does the risk also not come from the non-nuclear countries at present, but who have aspirations to become nuclear armed, or even terrorist groups? Because even if countries did get rid of their nuclear know-how, it still exists, and people still know what you can achieve with this, and therefore, even if countries did have no nuclear weapons, others could still elaborate them and then use them, and we would be defenceless.
That's a very fair comment, and one has to work out how that can be avoided to some extent. This will be a long way down the road, one would have to say, when we're already sort of getting used to the idea that on balance it is better to get rid of all stock and do it under some sort of international control. We're nowhere near that at the present. In fact, at present, the United Nations as a body is in one of its weakest periods, partly because of the attitude of some leaders, both from the East and the West, one I have to say. But I think the possibility of making progress is there, and in small ways, like the example I gave at the end of the Cuban Missile Crisis, when frankly the East and West leaders have really been shocked at how close they got to war. And we now know that we were much closer at the time of Cuba. And as you pointed out, there was the Able Archer incident, which again scared people a lot. So I think it's a difficulty, it's one you have to face, but that is no reason for not trying to rest with the problem that we are capable of destroying ourselves almost on a global scale, and that is something for which we have to aim.
The conversation we're having assumes that a massive power like America and a massive power like China or Russia decided to start lobbing nuclear weapons at one another. But what about if the path was slightly different? The example you gave, India, Pakistan, or currently what's going on with Ukraine and Russia. What would be the consequence if Russia decided to use some tactical, smaller weapons just locally in Ukraine?
I think that the real problem that Western countries would face over an example like Ukraine is that if Putin was to do that and just do a demonstration shot, and there is a view that the West would almost have to react like for like. There is another view that there's enough sense around for people to realize that if Putin did that, it would damn Russia itself to being almost a global outcast if it didn't get retaliation from a similar level. In other words, if the Western countries like the United States held back and exposed the strongest possible economic sanctions, would that actually mean that ending up with this, Russia would actually be in a worse position? So it's a complex situation, but again, yes, this is the kind of dilemma you would face. But if the major aim, as I would repeat, is actually to avoid a global disaster at some time in the future, then there will be risks that have to be taken. There will be difficulties that have to be ironed out. And now is the time to do that.
Paul Rogers, he's at Bradford University. Now, as we've been hearing throughout the show, nuclear weapons have thankfully been used just twice in the history of conflict, and those measures that Paul was mentioning will hopefully mean that the world's nuclear-armed nations will continue to remember that meeting jaw to jaw is better than war, as Winston Churchill famously put it. That's it for this episode, but do join us, of course, on Friday for the latest science news. We'll be hearing about a new brace of satellites that use reflected GPS signals to interrogate the Earth's surface, and also how we can stop seagulls from stealing our chips at the seaside. Apparently, it might be as simple as shouting at them. Isn't science marvellous? Meanwhile, if you enjoy what we do every week and you'd like to help to keep the Naked Scientists on the road, do please consider making a donation. You can do that safely and simply at nakedscientist.com/donate. You can, of course, also leave us a review, which helps too, on your favourite podcasting platform. Follow us also on Instagram, LinkedIn and on X. The Naked Scientists is supported by Rolls-Royce. I'm Chris Smith, and from all of us here at the Naked Scientist team, thanks for listening, and until next time, goodbye.